and our group did the Clapeyron experiment. So just a background of the experiment. So the whole objective of the experiment is to find the latent rate of vaporization of water at different points. So we essentially look at between 0 degrees Celsius and 100 degrees Celsius, find out what the latent heat of vaporization is throughout, looking at specific enthalpies, pressures, temperatures, things like that throughout the experiment. And then the whole point is to kind of measure the experimental results with our ideal results, or what would be in the steam tables. So the whole basis behind the experiment is the Clapeyron equations. So first one being dP of saturation, so your saturation pressure, over dT. And we use the run on the right, so your specific enthalpy, so essentially the enthalpy at the vaporization state, over your temperature and specific volume. And in our case, we just assumed that this was an ideal gas, and it can be a safe assumption, especially for this one. So it changes the specific volume to a t squared times your ideal gas constant, which was 450 for steam. So next, looking at the equipment setup. So there's a lot of different things going on. First, we have our flask, which actually holds the water that will be boiling. The second is the hot plate heater, which heats up the flask to make it boil. Then there's a type K thermocouple, which will measure the temperature in the water during the operation. We have a pressure transducer and a pressure gauge, which measures the pressure of the system throughout the operation. We have an air bleed valve that controls just the bleeding if we needed, relieve some pressure. Vacuum control valve, which controls the vacuum in the system. We have a centrifugal pump, which will pump water and really pull a vacuum in the system, which is kind of what we're trying to go for here. Water reservoir that holds the water for fluid circulation. And then finally, our computer system that gives us the resultant data that we need for the experiment. So next, the experimental procedure. Like I said, we placed the flask, and for our experiment, we used the boiling beads. We filled it with 2 inches of water and put it on the hot plate. Then we pulled a vacuum by turning on the pump, relieving the vacuum in the system, and we got it as close as we could to a vacuum without, getting, I don't know. So we got it to around 1 psi, which was pretty close to a vacuum. And then we turned on the hot plate to our max temperature, let the system run. It took about 5-10 minutes for it to get from room temperature all the way up to 95 degrees. And then finally at 95 degrees, we shut off our valves, stopped the data, and then turned off the system. So the first thing I did was plot the pressure that we got as a result of the experiment with the temperature during the experiment. So as you can see, the blue line shows our experimental data. And then I went ahead and went to the thermo tables and pulled some of the tabular data that they had. And as you can see, it lines up pretty closely. So this just shows that it is similar, and the experimental results that we got closely measured to the ideal results in the tables. So next, I went through a few different procedures to calculate specific enthalpy. And they get harder as each procedure goes on, and they're supposed to be more precise. So the first one is to make estimates based on the local derivatives. So like we saw on the Clapeyron equation, you have your dP dt. So essentially what I did was take 2 different ranges of pressure. So if I was looking at 50 pounds, I would do 40 to 50 pounds or something like that, and then get the values within that. The second procedure was to fit the data. So conduct a linear regression, get the equation, and then take derivatives to find our specific enthalpy. And then finally, rearrange the equation and use the Excel tool called Analysis Toolpack, which will do a data analysis, run a linear regression, and then we can solve for specific enthalpy like that. So with the first procedure, like I said, I found dP dt at 4 different temperatures. So I did 50, 60, 70, and 80. As you can see, the results from this compared with the ideal results that I found in the thermo table were completely off. And as you can see, at 50 degrees, we got around 1,500 kilojoules per kilogram, whereas the steam table showed almost 1,000 more in that number. And then there is no trend in the data whereas the graph on the right is what it should look like. As you can see, there's a downward trend with your latent heat as temperature goes. So these numbers are way off, and this wasn't a good method to solve specific heat. The next procedure, like I said, was conduct a linear regression on the system. And since the graph that we got was a pressure versus temperature graph, all you had to do was take the derivative, and that would get you your dp dt. And then rearranging the equation, you were able to find the specific enthalpy of the system. And as you can see, the results that I got from this system were a lot closer to our ideal results, but still weren't close enough. Go ahead. And the last one I did was this fancy like Excel analysis. So essentially I took the natural log of the equation, and then that gave me 3 different constants that I used the data analysis tool in Excel to get, and then converted that to a linear equation. And similar to the graph that we saw earlier, there is a downward linear trend, so it kind of matches up with what we're looking at. And as you can see, the data closely mimics it as opposed to the other procedures, and there is that downward trend that we're looking for. So in conclusion, like I said, procedure 3 had the best results, with procedure 2 and then procedure 1 following it. None of them directly matched the thermotables, but procedure 3 was the closest one. And then as far as recommendations, so whenever we pulled the vacuum, the most important thing was to get the seal on the flask. And I think in the future, if we could pull a better vacuum or get a better seal, our data results could be better. And that's it.